So this week's note, I will use this one, which is uploaded in the website. So it is a Word file. Okay, so copy. Right here, paste it. All right, let's open it. So this one summarizes chapter 5. Okay. All right, so I will use this one for today. So if I can cover this by today, then you guys are ready for homework number 4 and midterm. All right, so chapter 5 talks about source coding. The source coding, you have two kinds. First is distortion-less. The other one is with distortion. Okay, just like with distortion, that type of thing is what you have learned in undergraduate class with the sampling theorem, right? So you need to first cut off at the maximum frequency, a certain maximum frequency, and then you can sample this analog source with a rate of 2 times of the f max that you have learned in class, right? That's source coding with distortion. Okay, but this one is without distortion. Okay, so so chapter 5 says distortion-less data compression, and basically we talked a little bit about this in chapter 2, where we learned that we want to use longer description for what? Less frequent words, right? And short description for very frequent word, right? So that's the intuition that we developed in chapter 2, right? And basically our goal here is we want to find out the minimum possible description length, right, with a particular coding method. That's what we are trying to do. So that one is what is the expected length of code, right, that are very close to the entropy, right? Or if you consider a vector or a sequence, then entropy rate, right, should be, the description length should be very close to, as much as possible to this entropy or entropy rate, right? Entropy, if you just use a symbol by symbol coding, but entropy rate, if you talk about a sequence of length n, right, as you let n goes to infinity. All right, so that's the chapter 2 material, and then here we are at chapter 5. So the code is a code is formally defined as a function. Okay, so it's a map from, let's say, space x to d. Okay, d is a deary string. So deary string here means that if you have a binary sequence, binary strings, then these strings are made of ones and zeros, right? If it is a ternary strings, made of 0, 1, 2. Quaternary, 0, 1, 2, 3, and so on, right? So that is this space, and this space is just random variable space, okay? So code C is a mapping from X to D star, okay? That's what it is, all right? And that is basically it. And when we talk about expected length here, let's say you have a code, and then expected length of your code is defined to be this, okay? Expectation of random variable Lx, okay? And then Lx is nothing but description length of your outcome x, okay? Basically that's it. And now we can talk about when you do coding, right? You want to be able to decode, right? If you just code and then if you don't care about decoding, that's nothing, right? So we have to think about mapping, but we are interested in such a map that can be demapped, right? So that we can come back to X, right? From code word, right? Encoding, decoding, right? Encoding is going from X to D. D to X is decoding, right? So you want to have a decoding. Then basically what is the requirement for the map? Can you allow many to one map? No, right? So you need to have a one-to-one map, right? If you have a one-to-one map, the language this textbook uses is non-singular, okay? That means decodable, okay? Or uniquely decodable, right? That is the language. So in this chapter, all you have to learn is how to use the language that Carver and Thomas uses, okay? Other than that, nothing much difficult, all right? So non-singular code, right, is formally defined this way. Code is said to be non-singular if every element of X maps into a different string in D star, okay? D star is that code word space, okay? So if Xi, Xj not equal to each other, they should map to different code word. Okay, that's it. Okay, and then basically rest of them falls through. This is just the Wikipedia definition of one-to-one function and one-to-one correspondence and so on. So that you can review it. Okay, and so non-singular code is a map of a particular random variable x. Okay, but now we want to move on to the area of sequence, okay? What about if you have not just a single letter, but sequence of letters, okay? If you have a sequence of letter, the language Carver and Thomas uses is uniquely decodable code, okay? So uniquely decodable code means decodable code, right? Uniquely, right? But here we are talking about sequence, okay? Then can we concatenate the symbol by symbol encoding, encoded output, concatenate them together, or should we separate with commas or space, right? If you have to do that, if you have to use commas and space to distinguish between code words, right? There are extra character that we have to use, right? Would that be efficient or not? Probably not, right? If it is possible, we can get rid of those meaningless boundary, right? So that we don't have to use commas and space. Then we can put these code words back to back with each other, right? Then it can be efficient, right? The length will be shorter, right? But in such a case, when we concatenate them together, what we have to make sure? Is it uniquely decodable or not, right? If it is uniquely decodable, then we call such a code uniquely decodable code, okay? That's it, okay? And then another thing that is a useful concept is, maybe I shouldn't hurry too much. So here there is an example, okay? So let's take a look at this. Code word for x1, because there is a mapping. So input is written inside a parenthesis, and then C here means a function that does the mapping, right? From x1 to code word space, okay? So here, that one is mapped to 0, 0. C x1 So this one should be x2, right? All right. 아, 이게 매트 타입이 여기에 설치가 안 돼갖고 바꿀 수가 없네. Anyway, so this should be x2, okay, right? And then code word, I mean the mapping from x1, x2 concatenated together is just outcome of cx1, which is 0, 0, outcome of cx2, which is 1, 1, right? So that's the meaning, okay? So that's the word extension means in this textbook, okay? So extension means we have used the mapping twice, and then outcome of the map is concatenated together, back to back, without space, okay, or commas. And then, this could be uniquely decodable or not. Let's say if you have this, you know that code book is this, can this be uniquely decodable or not? Do we need to have them separated with a comma in order to be able to distinguish? No, right? So this is uniquely decodable, right? What about this one? Another example. CX1, 1, 1, CX2, 1, 0, CX3, 1, 1, 0, CX4, 0, 1. Now you think about decoding this one. Let's say, how do I get rid of this space? Okay, I get rid of space so that I can see both of the pages together. All right, so 110, 110, this is given to you. Is this uniquely decodable? No, right? Because it could be this one twice, right? 110, 110, or 1, 1, and 0, 1, right? And 1, 0, right? It could be decodable into three ways, right? I mean, so 2 ways. Basically, in this particular case, we can parse it this way. Then when you do the decoding, it is x1. When you decode 0, 1, which is right here, that's x4. And 1, 0 here, x2. Okay? Do you know what I'm doing? Everyone, follow me, right? If you have any question, let me know, okay? So, what have I done so far? Code is a map. Code is a function, right? From space x to space d, right? Using the deity symbols. That's what I said, right? And then when you do the encoding, it should be decodable, otherwise it's useless, right? So we are talking about decodable coding, right? But the language that Carver and Thomas uses for a single map is non-singular code, right? If it is not decodable, right? Non-singular, right? But if we extend it to the concatenation of code words, right? Then even though I just throw you a sequence of code word, you should be able to decode it uniquely. That's what uniquely decodable code is, okay? All right. So that's what I'm doing here, okay? So it is, so in this particular case, it is not, this code here is not uniquely decodable code. Is this code non-singular? How many of you said this code is non-singular? Raise your hand. Non-singular one. Singular. How do you proceed to answer? Is it one-to-one or not, right? Is this one-to-one mapping or not? Huh? One-to-one. So it should be decodable, right? Just using one symbol mapping, right? I am using what type of, what is D here? What is D in this particular example? what is D here? 2, right? Right? These 2. Okay? Is this fixed length coding or variable length coding? Variable length. What are the lengths? Yeah. So code word length of 2 and 3, it is made up, right? So in this chapter we are just learning the vocabulary that Carl and Thomas uses. Okay, that's it. Okay. So here definition: uniquely decodable code. Code C, which is this map right here, random outcome to code word. That's what the map here is. So code C is said to be uniquely decodable. If we concatenate them together, still it is uniquely decodable. Okay? So it is uniquely decodable if kth extension is one-to-one mapping from xk to d star. Okay? And then k could be any number greater than or equal to 1. Okay? So we can talk about sequence of any length. So yeah, shortly, uniquely decodable code is a code which is non-singular even if it is extended. Extended here means even if we put them in sequences without commas and spaces, still decodable. Okay? If it is only decodable with the commas and space included in it, it is not uniquely decodable. Right? Okay? And there is an important class called the prefix code. Prefix code. So this is another language, right? You have to learn. Okay. So a code C is called prefix free code, but they just use a prefix code. Right? But the actual meaning here is that it should be prefix free. Okay. You will see why a moment later. Okay. Or an instantaneous code, right? If no code word is a prefix to any other code word, okay? So here, what it means is that, let's say there is a code word, right? And then there is another code word which has this as a prefix, right? Then it is not prefix free code, right? And let's consider this particular example. Let's say code is a set. So here 0, 1, 0, 1, 1, 0, 1, 1, 1, 0. Okay? So as you can see here, 1, 0 does not have 0 as a prefix. Okay? 1, 1, 0 does not have 0 or 1, 0 as a prefix. And then 1110 does not have 0, 10, 110 as a prefix. Okay? So what is the consequence of this type of coding? If you have a sequence of code word, put them back to back, concatenated together like this, what is the consequence? When you see 0, right? When you receive 0, you can do the decoding right away, right? Because there is only 1, right? Aha, this is first symbol, okay? 1, 0, aha, this is the second one. 1, 1, there is no code word, so you have to wait another digit, which is 0, aha, this is a code word. So as you can see a code word right there, then you can do the decoding. So that's why it is called the instantaneous code. What type of application this could be useful? Instantaneous code. What type of application? Real-time communication, right? Like a voice communication, huh? Real-time, because you can decode it right away. Otherwise, you have to wait until the end of the code word, the whole sequence. Then there will be a large delay, right? only at the last moment of the code word ending, then you can start decoding. Then you have to wait probably long time, right? If the sequence that you receive is very long, right? So, so this is useful in real-time communications. So this type of class is very important. All right. So is instantaneous, prefix-free code, or just prefix code, they are all the same thing in this textbook. And also another example, another name is self-punctuating, because as you can see, you can place the comma or space between any two code words, right away as you see the code word. All right. So prefix-free or just prefix code, or instantaneous, self-punctuating, they are all the same. Okay. All right. So here is the example. Let's see. There is an outcome which is 1, 2, 3, 4. I use this bracket as an ordered set, right? So here, when I have 1, 2, 3, 4, what I mean by that is mapping from first to first element right here. Okay, X to C, the order matters. So 1 is mapped to 0, 2 is mapped to 0, 3 is mapped to 1, 4 is mapped to 1 for code C1. Okay, that's the meaning. That's how I use this bracket here. Okay, now let me ask you a question. What type of code C1 is? Is it non-singular? Singular? Why? Many-to-one mapping, right? Okay, 1 is mapped to 0. 2 also is mapped to 0, right? 3 mapped to 1, 4 mapped to 1. So if you want to decode 0, it could be either 1 or 2, non-singular. It is not non-singular, so it is singular, right? You don't know what to do, right? What about if you receive 1? Same story, right? Should I decode it to 3 or 4? So this code is useless, right? This code is a map, right? But it's no good for us as a source compression, right? How about this C2? 0, 0, 1, 0, 0, 1, 1, 0. It is one-to-one mapping, right? One-to-one mapping. So if you receive any one of them, then you can decode back to 1, 2, and 3, 4, right? So if you receive 0, 1, 0, what is it? What is the decoded output for C2? 0, 1, 0. Huh? 2, right? 2. How about 1, 0? 4, right? Now let me ask you this. Is this singular? Code number 2, singular? No, not singular because it's one-to-one, right? Right? Okay. How about now C3? C2, let's say. Let's still ask you about C2. Is the C2 uniquely decodable? No? Can you find a counter example that is not uniquely decodable? 0, 1, 0. Okay, if you receive 0, 1, 0, it could be either decoded into 2 or what? 3 and 4. 3 and 4? 3 and 1, right? 0, 1, and 0, right? So this is not uniquely decodable. Okay, how about C3? Is this non-singular? Non-singular, one-to-one, right? Is this uniquely decodable? Basically, you can try it a couple of times and make sure that it is so, right? In this particular case, it is uniquely decodable, right? So you cannot find any combination that can be that can lead to decoding ambiguity, right? So it is uniquely decodable. And let me ask you another one. C3, so it is uniquely decodable, right? Is it prefix-free code? So what is the definition of prefix-free code? Any code word does not appear as a prefix to another code word, right? So let's figure it out. 10, does it appear any? So any sequence longer than 10 is this one. So 10 does not appear, but 11 does appear as a prefix to the fourth code word, right? So 11 appear right here. So it is not prefix-free code. All right, but it is uniquely decodable. How about this one? Prefix code, right? Nothing appear as no code word appears as a prefix to another code word. So 0 does not appear as a code word in the rest of the three. 10 does not appear as a prefix for the rest of the two, and so on. Okay, so this is a prefix-free code. Okay, so that's it. So chapter 5 is quite simple and easy. Okay, so here there is all codes, right? Then you can have a group of code that are non-singular, smaller set, right? And uniquely decodable code is even smaller. And then among them, prefix code is even smaller. Okay, so if it is prefix code, it is uniquely decodable, it is non-singular, right? And it is a code. Okay. So you could come up with a uniquely decodable code, but not prefix-free code, right? Which belongs to this area right here, right? All right, so that's it. So do you have a question so far? So we just learned the language, right? We just learned the definition of Cover and Thomas for the kinds of code, okay? And craft inequality, let me move on, okay? Craft inequality, this is about instantaneous code, prefix code, right? For any instantaneous code over a theory alphabet, okay, the collection of code word lengths, L1, L2, Lm, okay? So there are how many code words? M code words, right? And then each code word has a length in it. We call it L1, L2, and so on, right? Must satisfy this inequality. So D is what? The size of the alphabet that we are using. And then D minus Li, sum of this number from 1 to M, okay? Should be less than or equal to 1, where M is the total number of code words, okay? But this one is very simple if we consider a tree, okay? A tree, okay? So let's consider a binary tree, but you can extend it to deary tree because it's the same song and dance, right? So we can do code word assignment for prefix code this way. Let's say if it is binary tree, we can have first fork and the second one third, right? So if we have a length 3 binary sequence, it has 8 different possibilities at the maximum depth, okay? 8 choices. And then these 8 choices we can categorize this way. That is dependent of a code word. Let's say here. So if I choose this as a code word for length 1, okay, I will assign up for 0, down for 1, right? So this is code word with 1, 1, 0, right? And since it has to be prefix-free code, right, the descendant of this code word should not be selected as code word, right? If, for example, if I choose this one as another code word in addition to this, then obviously 0, 1 has a prefix of a code word which is 0, right? So if I want to design a prefix code, if I have chosen a particular node here in the tree, then all its descendants should not be chosen as a code word. Okay, so that's the rule. And this one, if I choose this as a code word, then no more code word, right? So I will not choose this as a code word, and then I will see one more, right? And then 1, 0. I will choose this as a code word. Then all the rest should not be chosen as a code word, right? From this guy. And then going further down from here, I have this and that, right? Or I could chosen this one as a code word. But in such a case, I would have only length 2 code word at the maximum. But here in this particular example, I wanted to do length 3 code word as well. So I have done this, and I have chosen this as a code word, right? But I haven't chosen this as a code word, so I just left it blank, white dot. Okay, so in this particular assignment, I have 3 code words. This one, which is 0, 1, 0, which is this one, and then 1, 1, 1, right? By the design, this is a prefix-free code, right? And then, in terms of craft inequality, basically, I need to consider depth, maximum depth. So in this particular case, code word length L1 is 1, L2 is 2, L3 is 3, right? So those are the 3 lengths for 3 code words, right, that I have designed, right? And then in such a case, I consider the word at the maximum depth. Aha, that means if I have length 1 code word, this there are 4 words with a blank, right? So they are not code words, right? And if I have length 2 code word, then I have 2 words that cannot be chosen as a code word, right? At depth 3, right? This could have been chosen as a code word, but on purpose I didn't. Right? You could choose this as a code word as well, but in this particular example, by my choice, I didn't choose it. Okay, I haven't chosen it. And then this one. Okay, so at the depth L max, I have descendant of code words and the code word, and then possible code word. Right? That's it. Okay. So if I consider only the descendant of a code word and the code word, right, then these 4, these 2, excluding that one, I have this. Okay. Code word or descendant of a code word. So if I do that, then basically I can write this number of words at this level is 2 to the minus 2, right? But that can be written as 2 to the 3 minus code word length 1, which is this. Okay? And this one, 2 to the minus 3 minus 2, which is the length of this code word. Okay? That is written right here. Okay? And then there are, in this particular example, 8 of them. So d to the power of 3, that is greater than or equal to descendant of code words, summation of them, and the code word. Okay? In this particular case, 4, 2, and 1. That is written right here. And then you divide both sides by dl max, then you have this Kraft inequality. Okay? So now, when do you have equality? So if you get rid of this type of white dots, right, you could choose that as a code word as well. Then what is the length? 1, 2, 3, 3. You have 2 code words of length 3, right? In that case, you have the exact equality, right? All right, so basically that's what the Kraft inequality is. All right, let's now move on. So you can read the proof, but that's we have covered already. Now we have this theorem converts to Kraft inequality. So given a collection of code word lengths that satisfy this inequality, the Kraft inequality, there exists an instantaneous code with these code word lengths. Okay, all right. So this is obvious by the design that we have done on the tree, right? On a tree, and let me give you a sentence. Tell me if it is true or false. Okay? Let me give you a sentence. Tell me if it is true or false. Let's say, given a collection of code with the code lengths that satisfy this inequality. There is a code with the Kraft inequality satisfied. Okay? This code is a prefix code. True or false? No? Is there any other answer?
It should be switched.
What and what should be switched?
If it is prefixed, that satisfies Kraft code.
Yeah, that's what we have here, right? This one. That's Kraft inequality, right? If you have a length of a prefix-free code, this length must satisfy Kraft inequality. But what did I say? So let me state one more time, right? So this first part, I say, right? There is a code which is satisfied the Kraft inequality. So it's a code. So it has a code words, and then whose code word length satisfy the Kraft inequality, right? That's what this statement right here. And then I say this code is a prefix code. True or false? Why? How? If you prove that, what do you need to do? If you want to prove that, yeah, counter example. Give a counter example, right? Right? How can you give a counter example? Yeah. So you can find out, code whose length satisfy, for example, of this tree, right? Like this assignment, right? Length 1, 2, and 3, but you can always choose another bad code, right? Whose length is 1 and 2 and 3. Can you give one example using this tree? 000, 000 for length 3, right? So obviously, it is not a prefix code, right? But the length satisfy Kraft inequality, okay? All right, so basically, that's it, right? So be careful with these things, right? And when you take a look at the introduction to mathematical thinking, you could have a different statement, right, which are equivalent with each other, right? So it is very useful to learn this basic second year mathematics major course, right? Because we use them very frequently, right? All right, so that's that. And here is an example. Let's say there is a list of code word lengths 1, 2 to 3. Is there a prefix code with such length? Can you answer this question? What do you need to do? Yeah, you have to apply the Kraft inequality, right? So, right? Pardon?
Construct tree.
Yeah, you can construct a tree, right? But here, since we have the theorem, right? If prefix code, any prefix code, right? Then Kraft inequality must be satisfied, right? So here, and the converse, if it is converse was what? We have to memorize a little bit. Huh? What was the converse? There, if you have a length, code word length, satisfy the Kraft inequality, then there exists, right? Because if you do a good job on assignment of code word on a tree, you can obviously find it, right? Because the Kraft inequality was proved on this tree, right? So if you have done a good job or a careful job, you can find the prefix code, right? So we can fairly say that there exists a prefix code, okay? All right, so that's what it is. And then in this particular case, then we can investigate if this code word length satisfy Kraft inequality. Then